Chapter 6, Section 3. In this part, we're going to look at similar triangles specifically. So kind of like what we did before with congruence, we originally learned what it meant to be congruent, and we dealt with all of those issues. After that, we looked into ways that we could prove triangles congruent without all the hoopla. We're going to do that again today. So again, kind of similar to similar polygons, similar triangles. Today, we're going to talk about specifically triangles and ways we can figure out if they're similar or not without going through all the sides, all the angles, see if there's a little bit of a shortcut. So take a look. The first thing we're going to look at is a postulate. And again, this is going to let us figure out what we know about similar triangles without all the hoopla. And yes, that is a technical term. So take a look. This is a postulate according to your textbook, and I would argue not really, but we'll go with it. So it's the angle-angle similarity postulate, or we're just going to call it angle-angle similarity. So again, we can use angle-angle for similarity, not for congruence. Keep that in mind. So here's what it says. If the two angles of one triangle are congruent to the two angles of another triangle, then that means the triangles are similar. And notice if we use the third angle theorem, then it would be very easy to show that all three. So if you know two angles, then automatically you know the third. And in this case, if we have all angles, then cool, they have to be similar. Proving this doesn't take a whole lot of effort. One way to do it, for example, if I could take QPR and say put Q at S, so we'll put a Q here, and then just redrew this triangle. Notice these angles match up, so the sides would match up. P and T match up. P, not B, P and T match up, and R and U, they match up. And notice we could say the converse of our corresponding angles theorem would show that these are indeed parallel. And then we could simply take measurements from there to show, cool, they have to be similar. So again, just a real quick, simple, informal proof, but it works. Let's talk about some other ideas that we can pull from that. So we have what we're going to call the side-side-side similarity. So if you use this in a proof, we're going to let SSS all on its own represent congruence, but the SSS similarity, you need to make sure you add that on. And here's what it says. It says, look, if we've got the measures of a corresponding sides of two triangles, if those corresponding measures are indeed proportional, then the triangles have to be similar. So for example, if this was A, B, and C, whatever those numbers are, and then X would represent our scale factor, cool. If they form a proportion, then ta-da, they have to be similar. And again, a proof for that, not terribly difficult, but it can be done. We also have a side angle side similarity. So again, if I have the included angle, and we've got two sides there, and those angles are congruent, and those side lengths form a proportion, then we've got similar triangles. Notice what we do not have is an angle side angle similarity. That doesn't happen. So again, angle side angle, not so much. Okay, so no joy there. But we do have a side and a side angle side similarity, and we'll use those in different situations to figure out, do we have similar triangles? And if so, what does that mean for our situation? Real quick, you might pause the slide. Not only are these properties true for equality, not only are they true for congruence, lo and behold, reflexive, symmetric, and transitive properties also work for similarity. I know you're shocked and awed by that, but it works. So again, just heads up, make that a point to know that if we've got any of these issues that we need to deal with, say in a proof, we've got them at our disposal. I'm not going to spend a lot of time there. I think we've beat that dead horse enough. So take a look. We're going to try and figure out if we can discover what AE and where is it? DE, see if we can figure out if they're the same. Well, notice we weren't told anywhere that these were similar triangles. It says parts of similar triangles, but we weren't told that. Let's see if we can work it out. I know that AEB and DEC have to be the same. They're vertical. I've got parallel lines here, which means angle B and angle C have to be the same because they are alternate interior. And then same could be said for our others. Remember, for angle, I only need that much to show that they are similar. But again, with our third angle theorem and also with these being alternate interior angles, we know that A and D also have to be similar. So cool, we've got similar triangles. That means we can start matching things up. So for example, I know that 2 corresponds with this 5 over here for CD. So 2 matches up with 5. And the 2 with this x1, so they're like items. And that means 5 with our x added to 5 business here. All right. So all we need to do is cross multiply, and we'll be able to work this out. So let's do that. So we'll take x plus 5 multiplied by 2, so that's 2x added to 10. And then we'll take x subtract 1 multiplied by 5, so that's 5x subtract 5. So I'm going to go ahead and subtract 2x from both sides, so that's 3x subtract 5 here and 10 on the other. Go ahead and add 5 to both sides, so that is 15 and 3x. And then, of course, we'll divide by 3. X is 5. Looks good. So then all we have to do is plug this in. So AE, if I take 5 subtract 1, that will be 4. And then if I take 5 in here, we will get 10. Looks good to me. All right, let's try another. Similar triangles have been used the world over. In ancient times, the sun was used to help measure different objects. If you want to research a mathematician by the name of Thales, if I could get my pen to write, there we go. He measured one of the Great Pyramids in Egypt by using the sun and shadows. He was able to measure his height and the shadow, and then measure the shadow of the pyramid at roughly the same time, and then was able to use proportions to figure out the pyramid's height. So yeah, pretty interesting situation. So let's look at this one. We're told that Nina was curious about the height of the Eiffel Tower. So there it is. She used a 1.5 meter model. So there it is, of the tower, and measured its shadow at 2 in the afternoon. Wonderful. The length of the shadow was a little less than a meter, so 0.9. She then measured the Eiffel Tower's shadow, so hopefully she was standing close to that end, and measured 240 meters. What is the height of the Eiffel Tower? Well, notice, we're going to assume here that the Eiffel Tower and the model sit at right angles to the ground. All right, so we've got that. And notice, we're going to assume that the sun creates those similar triangles. So that way we've got a side angle side situation. So side angle side. So let's start comparing those like items. So x for the larger triangle could be across from this 1.2 meter model. And then our 240 across from the 9/10 meters. And again, I'm not going to do full cross products here, simply because that's silly. Multiplying this through to x and then dividing it out again is silly. So I'm going to have x equal, I'm going to multiply 240 on both sides. So 240 multiplied by 1 2/10 over 9/10. And we'll see what we get. So 240, we'll multiply that by 1.2 divided by 0.9, and we get roughly, 320 meters as the height of the Eiffel Tower from this situation. I have no idea what the actual height of the Eiffel Tower is, but 320 meters is a long way up there. But again, anytime we have a situation like this where we're measuring shadows with the sun, we're going to assume that we've got these similar triangles. Or again, very, very close to similar, close enough for our work. All right, on we go. Some more examples. Take a look. In this case, we're going to determine whether each pair is similar and then justify our answer. Well, I noticed for number 10 here, all we're given are side lengths. So what we're going to have to do is make comparisons and see, do we have that same scale factor? Well, to go from 10 to 30 is a multiplication of 3. So if I can multiply by 3 with all the rest of these and get their corresponding sides, then it'll work. 15 times 3 is 45, so that works. 7 times 3 is also 21. So good. These are similar by side similarity. Looks good. Let's try 11. In this case, to go from 3 to 6, looks like it's a multiplication of 2. So if I can get 7 to 14 by multiplying by 2, we're good, and it looks like we are. So again, this is another side similarity issue. All right, well, let's take a look here. For number 12, I've got two sides and an angle, but notice the situation. It's not a side angle side scenario that we would be hoping for. This is instead side angle, all right, which doesn't work in any way, shape, or form for anything that we're doing. So in this case, we can say not similar, side angle, of course, does not work. All right, let's look at our next one here. We've got 120 and 20. So if we add those together, that's 140. We need 180 in total, so this has to be 40 over here. If I take a look at these, I've got 120 and 40, so that's 160. That means we need a 20 over here. And sure enough, 120, 120, 20, and 20, 40, and 40. So we could do this by our angle similarity. And it would work just fine. So cool. Definitely a similar triangle. Definitely similar triangles. Definitely similar triangles. Definitely not similar. Excellent. One more set, and then we'll be done. So take a look. We've got a couple of triangles here. We're asked to identify any similar triangles and then find x and the measures of the indicated sides. Cool. So let's identify the similar triangles. In this case, I know that ABE and CBD are the same. They're vertical. And then I also know, since we have parallel lines, that D and E are the same. They're alternate interior. So I can say that triangle ABE is similar to triangle, looks like CBD. Excellent. So we've identified the similar triangles. Find x. So here we go. So 3 on this side matches up with 5 on that side. And then our 2x subtract 8 matches up with our x added to 3. All right, well, let's do some cross products. 3 times x, 3 times 3, 2 times 5x, and then 5 times 8. I'll go ahead and subtract 3x on both sides. So that gives me a 7x. And I'm going to go ahead and add the 40 while we're here, kind of save some space. Divide, and we find that x is 7. So cool, we found x. And now we need the measures of the indicated sides. So in this case, I need to know AB and BC. So AB is 10. Again, 7 added to 3 is 10. And then we've got to take 7 times 2 is 14. Subtract 8 is 6. Looks good to me. On we go. Same story. So let's get our similar triangles. I noticed that A and F are the same. B and E are the same. So by angle, we are good. So triangle A, B, D. Notice not C, but D is similar to triangle A matched with F, B matched with E, and then D would have to match with C. Excellent. Let's see what we can work out. I know that BD is x subtract 1, and I know that CE is x added to 2. Wonderful. So let's set up our proportion. I know that 3 will match up with 8, and I know that x subtract 1 matches up with x added to 2. Cross products time. So 3x, add 6, and then 8x, subtract 8. We'll subtract 3x on both sides, so that's 5. We'll go ahead and add the 8 since we're here, so that's 14. And then once we divide out, we find that x is 2.8, or if you'd rather it be a fraction, 2 4/5. Your call. 2.8, again, if you're talking about a Google form, would be the easier thing to type in, and Google will accept it. So we need to know what BD and EC or CE are. Again, with the symmetric property, it doesn't really matter how we write it. So BD, let's start there. It says we're going to take 1 away. So BD is simply going to be 1 8/10. And then if we add 2 for CE, then it would be, again, 2.8 here. We would get 4.8 for CE. All right. And that's pretty much the long and the short of it, folks. Similar triangles, not a big deal. So remember, we've got angle as one way to do it, to prove that we've got similar triangles. We can use side similarity or side angle side similarity. And those are the tools we have at our disposal. If you have any questions or concerns, make sure you bring them to class. Let me know. Otherwise, get your work done and have a good day.